Now we are down to the final section of chapter 3, rational functions. But after that, we're going to slow down and talk about radical functions a little bit more. And that will turn out to be far more difficult. Let's begin rational functions and complete it quickly. After all this should be a review. Finding out an asymptote, well, rational functions typically have asymptotes, and then to find out is important to deal. And there are two types of asymptotes you have to find first, and then you may have to find out the third one, depending upon the situation. Here in this problem, let's begin with easier of the two, horizontal asymptote. When x is really big, does y approach some constant value? Well, when denominator has higher degree, then denominator gets much bigger when x is sufficiently large. So y is going to approach to 0. Or you can do something like this. Take highest order term for numerator and denominator. What do you have? X to the third power or x to the fourth power, which is asymptotically equivalent to the original function. So what do you have? 1 over x, that's going down to 0, which means the horizontal asymptote is y equal to 0. Here's the graph, and you can actually see the behavior. When x is sufficiently large, you see that we have asymptotic behavior toward the x-axis. From the left-hand side, it's difficult to see, but if I zoom out, yes, you can see that. How about vertical asymptote? Well, as you can see, there are a couple. And can we actually find out? Yes, by setting the denominator equal to 0, you can find out. When denominator is equal to 0, then that means if I get sufficiently close to that number where denominator becomes 0, I'm going to get some finite number in numerator over denominators getting very small. Consequently, I'm going to get something really big, either positive or negative. Either way, I'm going to get vertical asymptote. How do I get it? Well, factor the denominator. Factor it further. I have x plus 1 times x minus 1. Yeah, there we go. We have x equal to negative 1 and x equals to positive 1. Those are the vertical asymptotes. Excuse me. Oh, this is something I'll have to discuss a bit later, but now that I see the picture, let's discuss this. What are the multiplicities of x plus 1 and x minus 1? They're both 1, aren't they? They're both odd. Not coincidentally, we see the splitting behavior and sign change. When x is greater than 1, but pretty close to 1, then the graph is going up, which means positive infinity. When x is close to 1 but a little bit less than 1, the graph is going down, which means y-coordinate value is going to negative infinity. Why do I have this kind of sign change? Well, around the odd multiplicity, we are supposed to have sign change, don't you remember? It's like multiplying by negative to the odd power. So we have sign change there. So we have this kind of splitting behavior. And the same thing goes to x equal to negative 1. Let's see, how about this example? How do you find out asymptotes? Do we have horizontal asymptote? We don't, because the numerator has higher power. So when x is really big, then y will blow up to infinity. As you can see in this graph, which you can get through your handheld calculator or free software like Desmos graphing calculator, you can see something like this, and then there's no horizontal or even slanted asymptote behavior. There are vertical asymptotes though, and you can get them by factoring the denominator and then find out when the denominator becomes 0. 5, 6, and negative 1 respectively. They both have odd multiplicity. Consequently, we have this splitting behavior. Crossing odd multiplicity, you have to change a sign. And the reason, well, a little bit to the right, it was positive. Now, crossing the multiplicity and then approaching from the left, it's like multiplying negative to the odd power, so we have to change of sign. How about the next problem here? 3x cubed. Okay, in that case, if I take highest order term disregarding the rest, highest order term and disregarding the rest, I'll probably end up with constant 3, and that is gonna be y equals 3 will be my horizontal asymptote. And let's see, yes, from the first picture we see vertical asymptotes, and when x equals to 0 and no, excuse me, no, not x equals to 0, excuse me, x equals to 2 and x equals to negative 2, I can factor the denominator excuse me, and x plus 2, x minus 2, those are vertical asymptotes. But what about x equal to 0? As a matter of fact, we have x as a common factor in numerator as well, so we have cancellation. So even though if you look at the denominator alone, looks like we have 3 factors and 3 vertical asymptotes, because of the cancellation, no, we have only 2. And that's reflected on this one. And then the second picture is showing the horizontal asymptote, y equals to 3. How about the next problem? Again, not really. Yeah, this is rather trivial. You can work on it. Let me see. Does it have any interesting graph? Yeah, okay, interesting graph, but detail is pretty much the same. How about finding out intercept? That's when the numerator is equal to 0 for the x-intercept, or for y-intercept you can plug in x equal to 0, and well, kind of like this. Y-intercept is easy, plug in x equal to 0, and then we have 2/5, and the graph runs through 2/5, and the second graph shows it. And then for the other asymptote, take the numerator equal to 0, and then you have a couple of zeros, 1/2 and negative 1/2, and we have those 2 points, negative 1/2 and positive 1/2 in the second graph. So setting the numerator equals to 0, we get zeros. Setting the denominator equals to 0, we get vertical asymptotes. If we have cancellation, kind of like this problem, then you may not have some of those, and some of those from both numerator and denominator may disappear by canceling each other. You may have to be a little bit careful about those kind of things. Now let's see, do we have slanted asymptote? Okay, here's an example. X cubed minus x squared minus x plus 1 over x squared plus 1. Okay, here's an example of a slanted asymptote. How do I know this is slanted asymptote? Numerator has order 3, degree 3. Denominator has order 2, degree 2. So numerator has 1 higher. So this one is asymptotically equivalent to a linear function. How do I find out that linear function? By a long division process, and then kind of like this. You can use long division to figure it out. The quotient is x minus 1, and then the remainder is negative 2x plus 2. So y equals to x minus 1 is a line, and then we have this fraction which is getting very, very close to 0 when x is sufficiently large, either left hand side or right hand side. So asymptotically we are going to get y equals to this quotient, x minus 1. That's going to be my asymptote. Let's see, we have this kind of graph, and then, well, we have an asymptote, the same asymptote we found out. How about this kind of situation? Similar, third power for numerator, second power for denominator. So numerator has 1 higher power, so we expect a slanted asymptote. just divide by denominator either by long division or some other technique like computer algebra system. You get a quotient y equals 3x minus 1. There goes a slanted asymptote, and this fraction will approach 0 when x is really big, so we have an asymptote indeed. And here is the justification. That, and then when well, the middle one, I don't know what this one is for. I think I jumped ahead. So yeah, this is related to the middle picture is related to finding out the zeros. And then the last picture is showing the asymptotic behavior, slanted asymptote. It may be a little bit too advanced, but the asymptote does not always have to be a linear function or a line. For example, if you go over to this 1.1b, like that, then in this case, let's see. If I divide numerator from denominator, numerator by denominator, and this is my quotient, and then we'll have a what do you call, remainder, and the remainder over denominator will go down to 0 anyway. So this quotient excuse me, quotient function, which is quadratic function, will be the asymptote. So if I plot these two functions together, we have asymptotic behavior. Even though the red curve is not a line, we can still have asymptotic behavior. It's just that this is asymptote curve, not asymptotic line. Actually, this is a parabola. And basically the same technique is being used here. By polynomial division, the quotient is going to be the asymptote. It happens to be the asymptote is parabola this time, and the difference between the order is, say, 3, then the asymptote will be a cubic function. Okay, we have a couple of minutes left, and then let's see, solving inequalities, rational inequalities. We already discussed this kind of examples. Factor the numerator and denominator to find out all the zeros and vertical asymptotes. And then now you can see why we have to use hollow dot for denominator and then solid dot for numerator. Numerator is actually an intercept, but denominator gives you vertical asymptotes. So the asymptotes are not part of the graph, so we have to exclude those even though we have semi-inequality. Domain of those kind of functions, well, in that case, basically you have to set the denominator equal to 0 and then remove those. So it should be something like that. Okay, in the next video we're going to talk about radical functions and then their domains.